All right. Hi, everybody, and welcome to this month's Cosmic Conversation. Today, we have speaker Dr. Kelly Lepo here today to talk to us about the James Webb Space Telescope. So Kelly is an education and outreach scientist at Space Telescope Science Institute, and this is where she supports outreach efforts for the James Webb Space Telescope, and she received her PhD in Astronomy and Astrophysics from the University of Toronto. And during her time in Canada, she made numerous local and national media appearances to talk about everything from the 2012 Mayan Apocalypse to the super blue blood moon. She previously served as the coordinator of the McGill Space Institute and taught physics at Gonzaga University and helped build the Large Hadron Collider at CERN. So I will hand it over now to Kelly.
Okay, thank you for that lovely introduction, Jesse. I'm going to go share my screen. Hopefully this works. Okay. So yes, my name is Dr. Kelly Lepo. I'm an education and outreach scientist at the Space Telescope Science Institute. And Jesse invited me on today to talk a little bit about the first year of web science. She said I could talk about whatever I wanted, and I've been threatening, whenever anyone says this, to spend 20 minutes talking about stars. And I think I'm actually going to do that today. So we're going to talk about the first year of JWST science with a focus on stars. So it's from this rather unassuming looking office building on the campus of Johns Hopkins University that all this magic happens. This is the Space Telescope Science Institute outside of in Baltimore, Maryland. And it is the science home of the Hubble Space Telescope. It's a science and mission operations home of the James Webb Space Telescope, and it's also the science operations home of the upcoming Nancy Grace Roman Space Telescope, which means a couple floors above my office is the Mission Operations Center, the MOC, where scientists and engineers monitor the health of the James Webb Space Telescope. They send commands up to the telescope. They plan the schedule, both long-term and for the week, and they also downlink all of the data for the telescope. But they don't let me do that. I don't get to do that fun stuff, but I do get to do fun stuff like talk about web science with all of you all. So just to set the context, JWST, the Webb telescope, is currently 1 million miles away from the Earth at the special point called L2. It follows the Earth around as it orbits the sun, and it is so far out in an area where we can't service it if something goes wrong because it's an infrared telescope and it needs to be very, very cold. So we put it all the way out there partially to get away from the heat of the sun and the Earth and the moon. So infrared light is a type of light that's just redder than what our eyes can see. Webb sees from sort of the reddy orange bit of the visible light spectrum through the near infrared all the way into the mid-infrared. You can compare this to Hubble, which sees mostly visible light with a little bit of UV, ultraviolet light, a little bit of infrared light on the other side. So why look at space in different wavelengths of light? Well, every time you look at the universe in different wavelengths, you learn different things. So for example, we have here one of my favorite examples, some meerkats and a freshwater crocodile. If you look at them in visible light, you see the meerkats' cute little fuzzy tummies. If you look at them with an infrared camera, those little tummies start glowing. And that's because the meerkats are warm and they are glowing in infrared light. The freshwater crocodile is also glowing in infrared light, but it's not that much brighter than the ground. And that's because it's cold-blooded. So it's more or less the same temperature as the ground. The meerkats are warm-blooded. They're warmer than their environment. And we can see that just by looking at infrared light. And so the takeaway here is that you and me and the computer that I'm looking into right now, we're all glowing very brightly in infrared light. Anything that's about room temperature glows very brightly in infrared light. Okay, so one more piece of context, just so you can understand some of the images that I'm going to show you, is something we call diffraction spikes. And diffraction spikes are something that show up in all sorts of reflecting telescopes. And these are caused by two things. Number one is the shape of the mirror in the telescope, and number two is the shape of the struts. And the struts are those supports which hold the secondary mirror in front of the primary mirror. So we can look at the diffraction pattern caused by different shaped mirrors, and we can tell instantly what telescope took that picture. So you can always tell a Hubble telescope image from a Webb telescope image by counting the spikes on the stars. So in Hubble images, stars will have 4 spikes, and on Webb images, the stars will have 8 spikes, 6 big spikes, and 2 little spikes. And that is caused by a combination of the shape of the mirror. It's a hexagon shape, so you basically get 1 spike for every edge of your mirror. And also, you get spikes from the struts interfering with the waves of light. And so that gets you another 6-pointed star pattern. So you have these 2 overlapping 6-pointed star patterns cleverly designed by the engineers who built the telescope to partially overlap with each other and make this 8-pointed star pattern. Okay, with that context, we know that bright, small things like stars will have 8-pointed stars in Webb images. So we can look at this, the first science image released by Webb about a year ago. This is the Joe Biden image that was released in a White House press conference. And we can see the whole history of the universe in one image here, which is why I like this one a lot, even though its focus isn't on stars. But there is one bright star in the center of the image. We can see it has diffraction spikes. That's a star in our own Milky Way galaxy. And then those white fuzzy things in the middle are actually galaxies in a galaxy cluster. So galaxies are collections of stars and gas and dust and dark matter. We're seeing them here in a cluster of galaxies, and between those galaxies is even more gas and even more dark matter. And all of this mass is so big that it's actually warping the fabric of space-time. And we can see that because we have galaxies that are behind the galaxy cluster. They shine through the galaxy cluster, and we see these arcs. And these arcs are the light from those background galaxies getting bent and distorted and magnified. And the reason that we like to look at these galaxy clusters is because this magnification, this natural magnifying class, even if it is kind of a lousy one, allows us to see even further, to see more distant galaxies. But enough about galaxies. Let's talk a little bit first about how we're making these images. Because another question that I get all the time is, well, Webb sees infrared light. How can we make color images from it? Or even, are all of these space pictures fake? They're not, they're real. This is real data that we are looking at. So space telescopes are designed primarily for science, but we can actually use them to make really beautiful images as well. And we do this by shooting through a series of filters. And this happens actually in your phone or in a fancier camera, but sort of on the chip level. Webb is designed for science, so we physically shoot through different filters, which block out all but just certain wavelengths of light. And so we take the shortest wavelength filter, the bluest filter, and we assign that blue. We take the longest wavelength filter, the reddest filter, we assign that red. We pick somewhere in the middle and we assign that green. And then we pick colors in between if we're using more than 3 filters. And so you can see the result here is a full color image, an infrared image of a very famous Hubble scene, the Pillars of Creation. It kind of looks a little washed out here. And if you've ever shot with a fancy DSLR camera and then looked at the raw images, they kind of look like this. So just like you would take those pictures and import them into Lightroom, our image processors also do adjustments on these pictures to adjust the contrast and color and white balance. And in the end, we get the image on the right, which is our final image of the Pillars of Creation. And we make this really beautiful image, and that's all real telescope data. That's all real infrared photons that have been collected by the detectors and beamed back down to Earth as electronic signals. But we just, do a little bit of processing in them so we can bring out all of those details. So speaking of the Pillars of Creation, I said this was a very iconic Hubble image. And what we're looking at here are these dark, dusty pillars with new stars forming inside. the Hubble image is on the left. This isn't actually the first Hubble image of the pillars of creation. This is a later image, but it's really gorgeous anyways. But what we can't see is what's going on inside of these pillars because our view is being blocked by dust. And by dust, I mean like dust, like very, very teeny tiny particles of sand and things that are very close to soot. So we can't see through the dust in that visible light view with Hubble, but we can use Webb's infrared vision to look through that dust to see inside of the pillars to see the stars forming inside. And actually, if you look at the tip of the pillars, you see those red lava-like areas. And those are shocks caused by young stars pulling in the surrounding gas and then shooting it out into the nebula, heating up the gas around them. And then if we go to even longer, redder wavelengths into this mid-infrared view from Webb, most of the stars drop out. That's because stars usually don't glow that brightly in mid-infrared light. But what does glow brightly in mid-infrared light is dust. So we can study the dust itself inside of this nebula by looking at this mid-infrared view. Okay, let's look at another star-forming area. This one is called NGC 3324. It is a little bubble inside of the Carina Nebula. So inside, in the middle of this bubble, are a couple bright stars. And those bright stars are actually eroding the gas around them. They're blowing bubbles with ultraviolet light and winds. And we can see the edge of this star-forming nebula is still intact with a bubble cleared out in the middle. So we're going to zoom into the edge of the bubble. And what we see is this. This is the really iconic Webb image, the cosmic cliffs in the Carina Nebula. So again, right out of frame are those bright stars that are eroding away the nebula. We see those sort of misty, wispy things rising up over the mountain-like areas, and that's actually gas and dust being eroded away right now by those stars. There's lots of dynamic stuff happening in this picture. The bottom area, the mountain-like area, is actually, again, another dark, dusty, star-forming nebula, and we're seeing partially inside with an infrared light view, and we can see all of these stars forming inside. If we switch over to a different filter, this is emphasizing molecular hydrogen gas, we can actually see some of the outflows from these young stars. We can see jets and outflows and gas ramming into other gas and heating up and all of that cool stuff. Okay, another star-forming area. Gosh, there's so many of these. They're all beautiful. This one was actually, it's a object we are seeing here. It's a dark, dusty nebula, and we're seeing a jet shooting out. This is a visible light image from a ground-based telescope. So we see one jet from this star, that's that red wavy thing, and we see it impacting on the neighboring gas, and that's that blue shocked area. The black thing in the middle is a dusty nebula. We can't see the background stars because it's so dense that we can't see through in a visible light view. But let's switch over to Webb. And this image was actually released yesterday, and it's another one of my favorite images now. We can see the stars that are responsible for that one jet, and there's not just one jet, there are now two. So the star is blowing jets above and below its disk, that those jets are ramming into the surrounding nebula. And because we can see through the nebula, now we can see what's going on inside of that dark, dusty area. So that's really cool. Beautiful. Okay, another image. This one is another baby forming star. We actually don't see the star itself, but we see a line in the middle, and that's the disk that's surrounding the star. And the star is actually evacuating a cavity above and below itself. So the idea to have in your head is something like this. We have a star in the middle. We have a disk. The disk is pulling in gas. It's swirling around the disk and then getting ejected up and down. Okay, but we can't actually see that. What we see is the edges of the cavity glowing as stuff is ramming into it. So if we take that away, it looks something like this, which looks exactly like this. Pretty cool. Okay, moving on from star birth, let's talk about star death. So stars are born, they live a pretty boring middle-aged life, and then they die. So here we have two stars. This is sort of a diagram. at first, we'll talk about this and then I'll show you the real pictures. So we have a star. It's at the end of its lifetime. It's a massive star. It has really strong winds. It's blowing off its outer layers. And we're getting to the point where we're seeing an exposed core of the star. The star has a companion, and this companion is also pretty massive, and they're orbiting around each other. And at certain points in the orbit, the winds from these two stars collide. And for some reason, and we don't quite understand why, these colliding winds end up being a really great place to produce dust, soot-like dust. So we can make a computer model of these interactions, and the shell should look something like this. So we have this weird shape of a dust shell. And then we can imagine we make the dust shell, and then the winds of the stars blow the dust shell out a little bit. We make another shell, it blows out, another shell, it blows out. And so then the computer model says that we should see something that looks like this. So we see a series of shells, just sort of like tree rings. You want to see the real image? Here we go. What? It looks just like the model. This looks fake, but this is in fact a real image. And these arcs are real. It's not that just half of them are being lit up. The dust is just in these semicircular arc shapes. So the stars have an 8-year orbit, which means that if we count 17 shells, we have 130 years of soot-like carbon-containing dust. So this tells us that these massive stars at the end of their lifetime in binary orbits might actually be a source of a lot of the dust that we find in the early universe, which is pretty cool. And it's also I love spirals in space, and this is, oh gosh, really cool image. Okay, my last stellar death. This is a supernova explosion. This is actually an X-ray image of a supernova remnant called Cassiopeia A. So this is the remnant of a massive star which has run out of fuel. It implodes and then it explodes. And this explosion goes out and it shocks and heats the surrounding gas and dust around this star. Okay, so this is an X-ray image. This is showing you the hottest gas. But this supernova remnant emits at all sorts of different wavelengths, and Webb looked at it with its infrared eyes. And so we're seeing partially some shocked gas here. The outer stuff is actually dusty areas on the outside of the supernova remnant. And the coolest thing is this green thing in the middle. So the scientists who study this call it the green monster, and they don't know what it is. They don't know what this feature is. It's green. It's got these like bubbles in it. So what's making those bubbles? We don't know. So this is like a cosmic mystery. And this, as a scientist, is a really exciting place to be. We have this really puzzling image, and we're going to try to figure it out. So that is all I have for today. So the Webb's science themes include the life cycle of stars, which we talked about today, but also other worlds, including planets inside and outside of the solar system, the history of galaxies over time, and also the first galaxies to form after the Big Bang. So I only had time to talk about one of those themes, but I'm happy to have a conversation and talk about any one of those. So yeah, thank you very much for your attention.
Thank you, Kelly. That was such a great breakdown on the life cycle of stars and with Webb. I really love how you framed with the images too as you went along. So I'll open it up to the group now that we have Kelly here. Are there any questions you have on Webb, the mission itself, any other science themes you're curious about, or follow-up questions to anything you heard in the presentation? I see Tish is raising her hand, so go ahead.
Hi, Kelly. Hi, everybody. I just love everything that you say about describing these images. That's one thing that we hope to do in education, is to just take one really super image and understand it. Try to understand it. So here's one. Can you tell us a little bit about Maisie's galaxy?
Okay, Maisie's galaxy. Yes. So Maisie's galaxy is a galaxy in the CEERS field, which is one of the deep field study surveys that Webb is currently under, I think it's completed. I don't know. So it's a first year of Webb science deep field study. And so they're trying to understand what was the early universe like? What were some of the first galaxies to form after the Big Bang? And so Maisie's galaxy is a galaxy that's the furthest galaxy in the CERN survey. It's named after the daughter of the principal investigator of that survey. And so looking at this galaxy, it's very red, it's very small, and it's very kind of blobby. And so that's telling us something about what these galaxies were like. We're actually seeing more structure in galaxies in the early universe than what we were expecting. And we're also seeing more galaxies in the early universe than we were expecting. And we're also seeing a more sort of bursty star formation. So it seems like star formation is turning on pretty early and then sort of turning itself off and then turning itself back on again. So it's very early days for understanding the early universe, but those are some of the preliminary findings to come out of the CERN survey and Maisie's galaxy. But there are a bunch of other surveys which all seem to be kind of agreeing with each other right now.
The article I read said 13.4 billion light years away.
Well, we're seeing it as it was 13.4 billion years in the past. Right. When you get that far back, distances start getting really weird. So usually we avoid saying it's X light years away because the universe is actually expanding right now. So it's actually further away than that. But yeah, it's better to talk about time elapsed than distance. It gets less confusing.
And one more question, it's kind of a galactic question. Is it true then, is there enough data to say that the really distant ancient galaxies are more crowded and that there used to be a lot more and that they're starting to become scarce?
Let me see, what's a good answer to that? So in the early universe, everything was closer to everything else, just by virtue of the universe being more dense in the past. So what has happened over the history of the universe is space itself has expanded. And so all galaxies or clusters of galaxies have gotten further away from other galaxies. And actually, that's something that the Euclid mission, which has just launched earlier this month, that's something that they're going to be doing. Part of their science is to measure the average distance between galaxies over time to try to understand the expansion history of the universe.
Cool. Distances are really interesting. So I just want to thank you for doing this because you're so busy with so much to do. To take the time to talk to us was really kind of you. Thank you.
Oh yeah, I'm always happy to have these conversations.
Any other questions for Kelly? We have about 5 more minutes.
Well, I have a question if no one else does about the Cassiopeia image.
Okay.
And the monster. So you said it was green, but what wavelength is that actually in?
Oh gosh.
Is it in a visible, like a...
No, it is actually, it's an infrared color, right?
Okay,
so that entire image that I showed you with all different types of infrared light. And so again, it's like you pick the reddest or the longest wavelength, you color that red. You pick the shortest wavelength, you color that blue. You pick somewhere in the middle and you color that green. So it's like whatever filter was in the middlest filter when they made that image. And I don't know the wavelength off the top of my head. I'd have to look it up. I know, right?
Right. I just want to clarify because often we use the colors that we see in the images that we've created, right? To talk about them. And so that's still infrared, even though we're going to call it the green monster of what it might be, which it seems very exciting. Well, I put a little plug for folks that they can work with their own JWST data right now. It's not a star forming region, it's a galaxy. Sorry. We have to change it up. We've been doing a lot of star stuff, so they can play with their own JWST data and they can look at archive data, and we have some past JWST data in there as well.
All right. Well, there's no other questions for Kelly. I will not keep her here because I know she has to get on to her next meeting. But thank you all so much for joining us today. And this recording will be posted on YouTube shortly after, probably tomorrow or on Monday. But thank you all for attending, and I'll see you for next month's Cosmic Conversation. And that's going to have a special speaker from Girls Steam Ahead with NASA, and they're talking about their latest cookbook recipe. So do feel free to join us if you have the time. All right, so thank you all and have a good day. Bye.
And Kelly.
Bye.